Hello and welcome to part 1 of Dev Maths and Stats Refresher Course, Lecture 2. In this lecture we start to look at differentiation, which is the single method in advanced maths that you're most likely to meet most often during this year. Now, differentiation is all about finding derivatives. So in the first part we just look at the concept of derivative. What do we mean by that? Then there's a section on why the methods that we're going to learn work, how derivatives are actually found from first principles, and then we get on to the core of the maths itself, just using rules to solve different problems, and then finally there's some example applications to real-world problems. So we'll start off here with what is a derivative? Look at that concept. So in economics and social science we're very interested in what happens when one variable changes in terms of what's the effect of another variable, or the impact of the change in one variable upon another. So if you're studying economics, you'll meet that all the time. If you're doing impact evaluation, that's the absolute core of what you're doing. And we want to know what's the direction of change. As in the previous lecture, is it positive or negative if I change one thing? But we can also ask, what about the size? So if you increase the education budget, what's the likely effect or impact on agricultural exports? Would it be positive because if you educate farmers more, they're going to be more efficient? Or would it be negative because when people get more educated, they're not interested in farming anymore and they turn their backs on agriculture? So that's the positive negative, but we also might want to be thinking about the size of the effect. So for every 1 million extra you spend on education, how much will exports grow, or how much will they shrink? If you go back to this function notation, which I introduced in the previous lecture, if you suppose that agricultural output depends on many, many things, if just one of those things is government education spending, then we can write agricultural output like a function like this. So all other factors and government's education spending. So the question here is, if we just increase this one argument, government education spending, by a single unit, what would be the change in agricultural output just from that change if you kept everything else constant? Now, this is what derivatives can help us find. So you can find out what happens as you change these by small amounts by finding the derivative of this function. The process of finding the derivative is called differentiation. So the derivative is another function that tells you what happens when you make a small change in the argument in the original function. So tomorrow we're going to look at the more realistic situation where there are many, many variables to consider. We'll start off today by just thinking about functions of one variable. When we have one variable, a common way of writing derivative is just to use a dash. So imagine just for today that agricultural production just depends only on education. So forget these other factors. Agricultural production depends on education, so A is just a function of G like this. A is a function of government spending education. Then if that's the function A, the derivative function will be written as A dash, and that would also depend on government education. So for any value of G you start with, so whatever government education spending is this year or today, A of GE tells you what's the level of output we expect from that. A dashed of GE tells you how much would we expect that level of output to change if we were to increase government spending on education from that level. Okay, now that's in words. Now many people, I know many people find it easier to have some sort of visual intuition. So we're going to look at some graphical demonstrations of that next. And there's a collection of those which should be linked to here. And you can follow those. It's probably best if you explore these in your own time, your own pace, but I'll pretty quickly mention some of the highlights of these. So if we go off to this list I've got here, it's made on an excellent system called Wakelet that actually collect together these related links. I thoroughly recommend it. So the first one then is just about the very basic idea of what's the gradient of a straight line. So we visit that. For a straight line, the gradient we're looking at, how much does y change when x changes? And in the simple maths revision we had yesterday, when we had these straight lines like this, that's the general equation. And this m should stand for the gradient, and c is the intercept on the y-axis. So here we've got an example where c is 2, and here the gradient is 1, because the definition of gradient is every time I go one step in the x direction, how many steps do I go in the y direction? So here, every one step x gives me one step y, so the gradient is 1. So the equation here would actually be y is equal to 1x plus 2, or in other words, y is equal to x plus 2. We can change this slightly by increasing the value of m. So let's try and slide m up to 2. There we go. So in this situation, m is now 2 because for every one step I go in this direction, I go up 2 in this direction. So here y will be equal to 2x plus 2. The gradient is now 2. And you can make it steeper, make it go negative. So here for every one step in this direction, I go down 1.3 steps. So the gradient is negative 1.3. The calculations are over here. So that's for going just one step along. This diagram is a little bit limited because in many times we want to go more than one step. So we need something more general than that one. So we look at these others. This one here gives you have to scroll down for it and wait for a moment. It is. So you just have two general points, and we're trying to find the gradient of this line that goes between these 2 points. At first glance, it looks like the gradient is 1 because we're going up 1. But remember, the definition of gradient is how many do you go up for every single step in the x direction? How far do you go? So this is the gradient here. Or in other words, here. We can calculate by dividing this 1 by the number of steps in this direction. So divide the 1 by the 3, and you get 1/3. So it's going 1/3 step upwards for every step along. Sometimes this is written as this increase in y is called the rise, so it's equal to the rise divided by the run, and the run is the increase in x. And the third one is very similar to that, but again slightly more. So it gives the calculation more detail here. Oh gosh. So here I'm going up about 15. The run is 30. I'm going up 15. So for every one step along, I'm going 15.5 divided by 30.2, 0.51, about half is the gradient here. So if you're writing this out, if you have a line that looks like this, then if I go along a certain distance in x here and go up a certain distance in y here, then the notation that we use for this is that delta x, you'll see this a lot, if x is the distance along here, delta x, this is a Greek d, means the change in x. You'll see this all the way through the course. When you see a variable changing, delta will mean the increase in that variable. So this is delta y, otherwise known as the rise and the run, and the gradients. I'd like to give this as an excuse that my handwriting on a computer is very bad, but when you meet me at the actual whiteboard, you'll notice like this. Not an awful lot better. But that's the formula. So it's delta y divided by delta x gives you the gradient for a straight line. Okay, so far so good. Let's go back to our collection of links. Now, the next step is to look at what happens when we're talking about a slope. Well, when you have a slope, the gradient of the slope at any individual point is defined by what's called the tangent. And the tangent, remember from your basic maths, is just a line that touches the slope at that point. So at this point A on this curve, the gradient of the slope here is the same as the gradient of this red tangent line. So here it would be 1. But in this, if I move even slightly this direction, you should be able to tell will the gradient rise or decrease. So just predict that, and if we slide this along, you'll see that the gradient is increasing all the time. So one thing that's tricky is that the gradient increases everywhere, so it's never the same, it's always changing. And on this side it's negative, because if I increase x by 1 here, I go down 3, so the gradient is negative 3. So you need some way of getting at these numbers so you can work out the gradient of this tangent line. And this is what derivatives and calculus and differentiation will let us do. So that's what the definition is of slope applied to a curve. Don't panic when you see this one, because if you're not that fond of trigonometry, this is a graph of sine x. As far as I know, in social science, impact evaluation, there isn't really any application of this. I'm just using it because it's useful to show a pattern of many rises and falls. We can see as we move along, what happens to the gradients is that it's quite steep, then it becomes less and less steep, and then it becomes negative and very steep negative, and then steep positive, and so on. And you notice that at some points it's actually completely flat, like here, and again it's here. So the gradient is 0 at certain points, which actually turn out to be these points here, which is very useful. So that's how the gradient is defined for a curve. Now, if you're thinking about, back to this definition, the problem is then, how do you get some numbers like this, which we can then use for this calculation? So if you're just looking at a graph, where do you get those numbers from? So this is a couple of visualizations showing how that works. What we have to do It's the wrong one first. This is the simplest one. Yeah. So what we have to do is, starting with a point like this, we move along a certain distance. So here we've moved along 1. And because we know the formula of this curve, we can work out exactly what the distance is here by substituting into the formula of the curve. So we can work out what this is and what this is, and divide this by this. This gives the gradient of the red line. Unfortunately though, that's not the same as the tangent. But we can get closer to the tangent by making this distance here smaller. So we make it down to here, that would be better. So we have this divided by this, that's better. That will give you a better approximation. And the smaller we make the delta x, the better approximation of the tangent gradient we get, until we get to here, when delta x is 0 and we get the exact tangent. Of course, there is a problem with that we'll meet in a moment. And this shows the same thing done on a more general graph. So here you can change the distance between here. This is the point we want to know the gradients at. This is the point slightly further along. We change the distance. So here h is the distance we're going forward. So if we make it quite small like that, then this is the gradient's fairly accurately captured. So we can see that it's very, very steep there. Here but notice it's not perfect, because here it looks like we come to the 0 point here, but here the gradient should still be positive. So it's slightly inaccurate. Make it more accurate by making h smaller. Less accurate by making it bigger. So that would give you a completely ridiculous picture, because here the gradient should be positive and it comes out negative. And the perfect picture is making h equal to 0. It's hard to do with the cursor there, something like that. Yeah, as we'll see in a moment. In the second part of this lecture. I'll leave you to look at that one if you like. That just picks up some more unusual cases. This one brings you to the idea of a derivative function, because what we have here is the same kind of situation, where we're interested in the blue graph. So we have the tangent line here, and here the slope comes out as 0.51. So every one step you go this way, you go 0.51 upwards, so that's the gradients. And again, if I slide along here, the gradient's going to increase. But notice this dot. Now this dot is actually, if you look, it's actually been put on here at 0.51. So the height of this dot is the same as the gradient function. This is the same as the gradients. And as I drag this along, this simulation will plot more and more points that show what the slope is at this point. So the height of this point here gives the slope of this line. And if you keep plotting those points, you get this. So we go along a bit. So now the slope is 0.97, so it's plotting our points at 0.97. As I move up more, it plots and it plots and it plots. So this line here is now the derivative function. Derivative because it comes from this graph here, derived from this function. It's derived from this graph, and the meaning of this line is showing you the gradients of this graph. So it gets steeper and steeper and steeper and steeper. At this point here, the gradient of the graph is actually the same as the height of the graph. So the gradient of the graph is the same as the gradient. The height of the graph is the same as gradient. If I go this way, I come to a point here where it's 0. So it doesn't plot it for some reason. If I go here, it's negative because here the slope is negative, so these points here are down below the axis to show that the slope is negative. And since this curve gives you the derivative, which is a straight line. Which brings us on to the best part, the most entertaining part of today's lecture, is this wonderful thing called the derivative puzzle, which I strongly encourage you all to have a go at until you can do it perfectly. The idea is here that we have some functions along the top, and we have at the bottom are some candidate functions. Now these are the derivatives of these functions here, but not necessarily in the right order, as somebody once said. Try googling that. Not necessarily in the right order. That's almost as entertaining as this. So here, for example, if you think about the gradient of this, the gradient here is negative. That means that correspondingly here, this is positive, so that can't be shown the gradient of that. This is positive, this is positive. So the only thing that can be shown is this, because this is a negative value here, shows you that the gradient is negative. And in fact, the gradient of this is negative all the way down to here, where it becomes 0 here. The same as this is negative, negative, and then it becomes 0. And then from here, the gradient of this is positive all the way to there. So that is going to be this one. Hopefully it'll say, oops, true. This one here, the gradient starts positive. Then here, the gradient goes smaller and smaller, always positive, and then becomes 0. And then it becomes positive again. So here, the gradient is never negative. So that rules that out, and it rules this out, because these go negative. So it must be this one. This shows where the gradient is highly positive, highly positive. Well, let's move it to here and we'll see. So the gradient here is always positive, and here it's always positive, and just here the gradient is 0. Just leaves a couple of other ones to get right. Here the gradient begins positive, falls down to gradient 0 here. Now the gradient is negative, falls down to 0 here, up to 0 I suppose, and then here it's positive. So it goes negative, positive, negative, and then positive. So it must be this one, positive, negative, and then positive with 2 0 points. So that's there. And this one must be this one because, by elimination, or because the gradient goes from negative, it's always positive gradient here, 0 gradient here, negative gradient here, positive, 0, negative. So if you can do this and reliably match them up, then, yes, good, 10 out of 10, then you'll understand this very well. And you can just press load no, it generates some slightly different ones each time. Another thing you might notice is that this is a kind of quadratic type of function. Now here we have the derivative is linear. This is quadratic, this is linear. These two are cubics, but here the derivative function comes out as quadratic. And that's an important pattern that you might spot. So press load new and have another go until you can do it. Well, that's the more interesting one. Okay, so enjoy that. Don't enjoy it so much you don't do your homework or forget to eat, but do have a go at it. So that concludes this part. So next time we'll move on to the idea of how you find these derivatives from first principles. But that's in the next lecture, so thanks for watching.